All right, everybody. Thank you for coming today. Today we'll be presenting Pennant, which is a cloud-based collaborative computational notebook. So Pennant runs in browser and allows users to create cells for text and code. Users can execute code cells on our cloud-based execution engine. Notes and documentation can be written in formatted markdown cells. All of this happens seamlessly while collaborating with multiple peers on the same notebook in real time. We face the two primary problem spaces: real-time collaboration and remote code execution. This presentation will discuss the trade-offs of the available technologies to address these challenges. We'll also discuss the inherent constraints of our use case. And finally, we'll discuss the build process as we iterated up to the alpha release. So computational notebooks are a tool that allows users to write code and documentation side by side in what's known as literate programming. Most common use cases for computational notebooks are for big data analysis, machine learning, and data visualization. On the left here, you can see a screen capture of Jupyter notebooks. Jupyter notebooks are synonymous with computational notebooks. So this is an example of a fully featured, mature notebook interface. It's a Jupyter notebook set up as a tutorial for processing large audio data sets to train a machine learning model. You'll notice the directories of data input on the right. There's a considerable quantity of data to be processed. In the left, we can see a large code cell, which may take a long time to execute. Notice the tutorial text is included in the text cell below the first code cell. Further down in the tutorial, there's a cell which visualizes a specific example from a large set processed in the previous slide. Notice how I'm able to change trivial details in this cell and run it over and over without running the time-intensive first cell again. The result of the execution of the first cell are persisted to a stateful execution context. Now I'm free to access that execution context in these subsequent code cells. For this project, we wanted to leverage the power of the notebook interface for educational purposes. With Pennant, code snippets can be transformed from experimental spikes into fully documented and easily teachable code. We wanted to support professional notebook users and developers looking for a JavaScript peer programming tool. There are other browser-based computational notebooks. None of them match our use case exactly. Only a few notebooks support multi-user collaboration. Jupyter Notebooks has been stumbling in their implementation of collaboration for almost 10 years. Building a performant collaborative application is also technically challenging. Collaborative applications can consume more compute power and memory than is necessary on their client browsers. Python is also the default language for most computational notebooks. Notebooks which support JavaScript tend not to support standard JavaScript. Here we can see the network tab for a different browser-based notebook. The browser application is opening a streaming connection to the server for each code cell. The browser becomes sluggish as the number of cells in the notebook grows. Many notebooks require that basic idiomatic parts of JavaScript, such as variable declarations, initializations, and function definitions, must be handled in a non-standard way. For example, Observable, which is a visualization-oriented notebook, disallows the use of the keywords let and const. So we could say that the user needs to write an observable flavored JavaScript, not standard JavaScript. For Pennant's educational use case, we need students to be able to use standard JavaScript. The particularities of JavaScript, like variable declaration or function hoisting, present difficulties for a notebook interface. With a notebook interface, we have code being split into cells. We can run every cell in the notebook in order, just like a script. The difficulty arises in that notebooks allow cells to be run independently in any order. The cells on the left and the cells on the right contain the same code in the same order. It's an initialization of a variable, a logging of that variable, and a reassignment of that variable. Script on the left will only ever execute from top to bottom. The results will never change. The reassignment at the bottom will never be utilized. The notebook interface is not locked into this linear execution. In this contrived example, we could first initialize our variable by running the first code cell. We could immediately reassign that variable in the third code cell. And then when we log the variable in cell 2, we'll see the string bar. So we know that the variable state was impacted by our order of execution. So we can say that execution context is stateful in notebook applications. The context is preserved between cell runs. This will be explored in greater depth when we discuss the execution engine. Our top-level goals for Pennant were real-time collaborative experience, a performant user application, which is fast and preserves user data, and real JavaScript, so that users don't need to learn a Pennant-flavored JavaScript in order to begin using the product. The recurrent technical requirements to meet the top-level goals are a low-latency architecture, safe execution of user-submitted code, and strongly consistent sharing of state across users. The needs of the collaboration service differed quite a bit from the needs of the execution engine. Judah will now take us deeper into the challenges of code execution engines for a collaborative application.
So our problem space is really two completely separate problem spaces. One's real-time collaboration and one's remote code execution. However, there's a really interesting cross space at the intersection of these two, which right now is not only being explored by us, but also by large companies and large open source products. First, here are a few general challenges in the collaboration space. These problems are maintaining a shared state across all users, so all users see the same thing. Having minimal latency in sending and receiving updates, so users can see the same thing at nearly the same time. Resolving conflicting user actions. Think like one user deletes a paragraph while another user is writing in that paragraph. There are many ways of resolving that situation. And finally, showing the presence of other users on the document. Okay, now here are some challenges in designing code execution engines. A code execution engine is just any program that takes a user code as input and returns the expected code output. Now, the most important problem for all code execution engines is to be safe. Since we're giving client users the ability to submit code, this opens the door to accepting malicious or error-ridden code that can spill out to affect the rest of the program. Other issues we faced were in trying to optimize our code engine for speed and flexibility. A third issue, a relatively new issue for the space, but a growing issue for products like Jupyter, VS Code, Replit, among others, is to allow for multiple users to access, work on, and execute the same code from different machines in real time. This collaborative code execution is where our two problem spaces overlap. And this is where we were focused. Okay, now you might be thinking, okay, well, that's CoderPad. And it is, but CoderPad is not a computational notebook. And computational notebook engines are more complex and work differently than generic code engines. The differences are what make it so difficult for Jupyter to make their notebooks collaborative, despite trying to do this for many years. In CoderPad and most code collaboration, code can be executed in a stateless fashion, which means each time you hit play, the code can be executed anywhere, on any server, regardless of where your teammate's code has been sent. Each code submission does not access any shared data from any previous submission. So you can see here that the console log statement on the right has no access to the value of X from the first run. In Pennant and other notebooks, code execution is stateful. Each code submission needs access to the context from previous submissions. This means all code from a notebook needs to be submitted to the same engine instance. That means the same instance on the same server. Why can't changes in code execution context just be shipped from user to user like document updates? Nobody does this because it's extremely difficult or even impossible to send execution context from user to user. Therefore, code execution needs to be centralized on a server. This runs against Jupyter Notebook's model of code execution on a user's machine, but it brought us to our solution, which is cloud-based, not user-based, collaborative code execution. Just to make this clear, if two users were submitting code from the same notebook, and each time they hit play, the code was submitted to a different engine instance, the notebook would not work as expected. Here, user one is submitting his code, and it's going to one engine instance, maybe on their machine, maybe on a server. User two is submitting her code, and it's going to another engine instance, maybe on her machine, maybe on another server. Even though they are collaborating on the same document, and even though the output can be synchronized once they get it, the output is not correct. So that means that unlike text editor collaborations, where changes can be made on your own version and then shipped to all other versions, code collaborations require all changes be sent to and made on one central location. This central bottleneck actually benefits code execution engines because it ensures that the users share one history, one context in which they all run their code. However, this brings us back again to the collaboration space. Advances in document collaboration over the past 20 years have actually gone against storing one central copy of a document. Users instead ship small updates to each other, and they merge these updates into their own copies of the document as they receive them. Again, this model would not work for code execution because collaborative code execution relies on a centralized execution context that everyone submits code to. So our problem space is really two problem spaces: code execution and real-time collaboration. The intersection of these problem spaces has been explored by other companies and open source projects. And the needs of collaborative code execution set limits on our code execution architecture. However, we were in a better position than existing companies in that we were designing and building our solution from scratch. We could build the engine the correct way to run code collaboratively and weren't tied to any outdated models. I'll pass it off to Richard now for the implementation details.
Now I'll break down the implementation for our two problem domains. We established these guiding principles for most of our decisions and trade-offs. We wanted a performant user application. We wanted notebook state to seamlessly merge updates from other users without needing to use any sort of system of lockouts. And we wanted to use the most standard versions of coding language as possible. Shouldn't be a special variant of JavaScript specific to Pennant because we wanted this tool to be useful in the education sphere. We also wanted users to be able to store their notebooks in the cloud like a typical web application. This is the broadest overview of the Pennant infrastructure to keep in mind as we discuss the implementation. We have a service for our code execution engine. We have a web server for our single-page React application, as well as for user management. Lastly, we have the collaboration service, which will be responsible for the bulk of the state synchronization between users. All of these tasks could be accomplished on the same piece of infrastructure, say one virtual private server. But consider the specific needs of the execution engine and the collaboration service. The execution engine needs to be as isolated as possible to safely run user code. Putting the execution engine on separate hardware and interacting with it via API adds an additional layer of security against malicious code. The collaboration service has the highest bandwidth needs. It will require a constant connection to all users as document state and user presence data are sent across the network. Given the bandwidth and connection needs of the collaboration service, it is likely to need to scale before the execution engine. The execution engine is likely to need to scale before the web server. Beginning our build with these services separated out would reduce the complexity of scaling out from a monolithic structure later. Now we'll begin discussing the implementation of the collaboration service. It's not a given that the collaboration service happens on Pennant infrastructure. So let's take a second to examine that choice. One model which is available to us was a peer-to-peer model, in which updates from every user will be broadcast to every other user currently on a notebook. It would be the responsibility of the client applications to merge updates and maintain document state. The technologies underlying Pennant can support a peer-to-peer model. It's not strictly necessary that we have updates of state or presence and awareness touch a centralized piece of infrastructure. This would be the lowest latency solution because there's no intermediary node between users. So it also reduced the complexity of our back-end infrastructure. However, the peer-to-peer model doesn't meet our needs for security, as there's no way to control and sanitize user inputs. It's also less performant for users, as their browsers need to maintain multiple connections. Instead, we opted for the more conventional client-server model, where every update is sent from a user to our collaboration service and then relayed to all connected notebook users. This gives our team greater insights into usage patterns and application performance in order to facilitate future development. It allows us to implement more safeguards for users' submitted code. This does add an additional node and thus more latency into the system. Despite this, the performance is fast enough for an elegant collaborative experience. This requires more complexity on the back end in the collaboration service, but less complexity inside the client application. Now Marwan will discuss the implementation details of the collaboration service.
Thank you, Richard. So implementing real-time collaboration in our application was a fascinating journey, and I'm excited to take you through many of the steps it took to accomplish it. So first, I'll begin by discussing how we designed a unified structure that all users could interact with. Next, I'll dive into algorithms and how they have allowed us to ensure state convergence. From there, I'll move on to how we synchronize the shared data model across all users. Then I'll discuss how we handled multiple synchronization scopes, like different notebooks within the same application. Finally, I'll focus on the human aspect and how we implemented real-time presence and awareness. So let's start with the shared data model. So deciding on the right data model can significantly affect many parts of your application. In our case, the shape of our data could either simplify or complicate the task of managing state between multiple users. So imagine a scenario where concurrent updates are happening to multiple replicas. This can easily lead to inconsistencies. So we found ourselves asking, how can we allow multiple users to work on the same document seamlessly? And how can we resolve those inconsistencies that are bound to arise? So we obviously needed efficient algorithms for state convergence and conflict resolution. So the answer wasn't immediately apparent, but after some research, we found a powerful solution in conflict-free replicated data types, or CRDTs. So CRDTs are data structures that enable multiple computers to update a shared data structure independently and concurrently. They guarantee eventual consistency by automatically resolving conflicts, even if replicas differ temporarily. So CRDTs have many key properties. One of them is uniqueness. So every character is assigned a unique identifier, which internally is known as a timestamp. So first is the user identifier, the user who performed the operation, and second is an incrementing clock, which indicates where in the sequence of operations the operation occurs. So for example, the left diagram here shows the same user, user 1, executing two operations, both of which are insertions. So starting with F at clock 0 and then O at clock 1. And it's worth noting that this is a monotonic clock that increments with each operation or update and does not actually represent time. So then on the right, you see green box indicating that user 2 has executed an insertion of the character O at clock 2. So the result becomes foo. Now let's look at concurrency. So the CRDT algorithm handles conflicts uniquely, as seen in this diagram starting with WXYZ. So at clock 0, two simultaneous insertions occur between W and X by users 0 and 1. The algorithm prioritizes lower user IDs, executing user 0's insertion first and user 1's second, resulting in WABXYZ. And you might be asking yourself, why favor lower user IDs? The answer is that it doesn't really matter. We could prioritize higher user IDs instead, but what's important is to have a consistent rule and stick to it so that all replicas can resolve conflicts the same way and converge to the same state. So CRDT operations are also associative and commutative, meaning operations can be grouped and applied in any order. They're also idempotent, so duplicate or repeated operations don't change the outcome. And all these properties help to maintain consistency in distributed systems. They ensure that variations in the order of event delivery or repeated message delivery do not lead to inconsistencies. So our search for the optimal CRDT led us to YJS, which stood out due to its optimizations, currently ranking as the most memory efficient CRDT. So with YJS, we had robust conflict resolution, undo and redo management, and the ability to handle network partitions and delays. So if a connection is lost, YJS continues to accept local changes and will merge these with the global state when the connection is restored. And this is demonstrated on this in this video. So I have a notebook open in Firefox on the left and Chrome on the right. The Wi-Fi is currently turned off, so the browsers are disconnected from the network. On the right, edits are being made while offline, and then when I reconnect to the Wi-Fi, without any intervention, Firefox on the left automatically syncs with the edits made in Chrome on the right. So after designing our shared data model and implementing algorithms for state convergence, it was now time to move on to synchronization. So in this step, we had to bind our editor content with the CRDT and sync the shared data model across all users. So let's explore how we made that connection. So our app enabled a pub submodel that was facilitated by connection providers. So client-side providers handle everything you see and interact with within the application. They ensure every modification made by their user is communicated to the backend. Mainly, they're responsible for displaying updates in real time. Then we have the backend providers. So these coordinate real-time data exchange on the network. They receive messages from each client-side provider, process them, and then send them back out to all other active clients. Essentially, they ensure that everyone remains in sync. So in our app, each cell contained either a code editor or markdown editor bound to a YJS data type. And traditionally, in collaborative editing, there's a one-to-one relationship between an editor and a WebSocket provider. This structure is simple and reliable, but can lead to inefficiencies in scenarios involving multiple editors or documents. So in this design, each editor requires its own connection, which can consume more resources and complicate synchronization between different parts of the application. But with Pennant, we took a more holistic approach. So by using nested YJS data types, we established a one-to-one ratio between an entire notebook and a WebSocket provider. This not only reduced connection overhead, but also resulted in a more efficient and cohesive system. So building on our one-to-one notebook to provider ratio, let's focus on how real-time communication happened between users and our backend provider. So while our system leverages the same client-side WebSocket provider to manage connections, each active client initiates its own WebSocket connection to the backend. So this setup efficiently handles real-time updates between users and the server and ensures that changes are both sent and received promptly. And for added persistence, we have an S3 bucket that takes periodic snapshots of the notebook. In managing many contexts, our providers encapsulated notebooks in separate rooms. So you can imagine rooms as metaphorical shared spaces where users can collaborate on a notebook. Each room is identified by a unique name, and all users connected to that room can interact in real time. And the backend provider takes charge of managing updates between those individual rooms without interference from others. So just to recap, so far we had laid the foundation of each notebook with a unified data structure for collaboration. We ensured all users see the same data simultaneously by implementing CRDTs. We used connection providers to create a unified view for all users, no matter where they are. And we handled multiple collaboration spaces like different notebooks by using rooms. So now all that was left was injecting life into the system by relaying real-time presence and awareness. So in real-time collaboration, knowing who's active and what they're doing is essential. This isn't just about seeing who's online, it's about understanding the workflow. So having an awareness protocol in place helps in relaying those visual cues. So this way, team members can identify potential conflicts and reduce the chances of overriding or pushing work that might be conflicting with others. And this awareness is facilitated by an object that's controlled by a specific protocol within our CRDT framework. This object communicates through broadcast messages. So the client sends an awareness message, which is broadcast by the server to all clients. And then the client also receives awareness messages originating from all other connected clients. And it's worth noting that all awareness data for any given client is ephemeral, but still uses that same WebSocket connection mentioned earlier for communication. So how do all of these pieces come together? So here's how. First, a user interacts with the application, for example, by typing. Then those actions get translated into transactions on the shared data model. Then the connection provider broadcasts the updates to all peers. Then every peer integrates the change into its own version of the shared data model. Finally, the user's view reflects this alteration and all versions of the app remain in sync. So by carefully selecting technologies, we were able to design a system that achieves almost instant propagation of changes. The main elements that made this possible were the use of WebSockets for communication, integrating memory-efficient CRDTs for handling concurrent updates, backend and client-side providers coordinating together and ensuring prompt communication across clients, and optimized data structures within YJS, which was our secret weapon in reducing potential latency. So with our real-time collaboration framework in place, we've set the stage for the next challenge, which was the implementation of our code execution engine. And to dive into the details of how we brought this to life, I'll now hand over to my teammate, Michael.
Thanks, Marwan. Let's begin by reviewing our requirements for code execution. We need code to run with the flexibility of a computational notebook, and execution environments need to be fully collaborative, meaning that collaborators should be working with a shared state and have consistent outputs. Lastly, we need robust security measures for executing untrusted code. We'll start a discussion with where to execute code. We had two broad options, client or server-side execution. Client-side is faster and provides features such as the rendering of front-end code. The leftmost diagram illustrates a multi-engine setup. All users execute code on their own browser. We know this isn't viable since multiple environments means executions and outputs can't be made consistent. The middle diagram is of a client-hosted model. Here, one user runs all the code for their group. This is collaborative, but variant user system configurations and network reliability become our chief concerns here. This made server-side execution our best option. Although it's slower and more expensive to host, we're able to create a more reliable, collaborative experience for our users. We had a few challenges with server-side execution, reducing code cell execution wait time, improving system reliability, and implementing security measures. We'll start with how we reduced code execution wait time. The unpredictability of user code leads to some problematic scenarios. In this example, our server receives run cell requests from 3 different notebooks. One of them is a recursive Fibonacci function call, while the others are 2 logging statements. What happens if our API receives the Fibonacci code first? Well, the request needs to be held open by the server until the code is evaluated, so other users have to wait. This leads to head-of-line blocking, dropped connections, and results in an overall unsatisfying user experience. And here's a worst-case scenario. Some notebook sends an infinite loop, and when it's executed, it consumes all of the engine's memory and causes the whole system to crash. Now no one's able to run code, and our API can't be reached either. All our front-end application gets are a series of request timeouts. Our solution was to decouple our RESTful API logic from code execution. Now, when a user runs a cell, there's no chance of our front-end code getting blocked. Our API server immediately sends execution requests to a respective notebook queue and then responds to the client with a token. From there, background workers dedicated to each notebook execute the code asynchronously. This asynchronous design enables our API to handle requests quickly and prevents head-of-line blocking. It also allows us to scale our code execution needs independently from our server, whether that's vertically or through the deployment of additional nodes. The other factor for reducing execution time is to minimize the number of cells that need to be executed per request. In other words, to run a notebook's code cell by cell rather than as an entire script. Unlike the short-lived processes used by conventional execution engines, Pennant's workers are long-lived processes that persist in execution context object in their memory. Cell contents are run as individual scripts against this context, allowing users to create new variables, functions, and objects, and any collaborator could reference those same entities in subsequent cell executions. This makes for a more responsive and faster experience by enabling stateful cell execution and by avoiding cold starts. Now we'll move on to system reliability. Our workers are containerized, which allows them to run concurrently and in isolation from one another. That means that long-running cells from one notebook won't block other notebooks from executing their own code. And more importantly, if any worker experiences a failure, others could continue functioning as normal. But it's also important to consider resource management, since all containers run on a shared host kernel. How can we keep the host machine healthy? We use Docker control groups to limit each container to only 100 megabytes of RAM and enforce compute limits. Script timeouts are also implemented by our code execution library. Lastly, we monitor system metrics so we can stop the deployment of additional workers under periods of high load. Altogether, containerization allows our users to execute code with minimal system downtime. Let's turn our attention to our final challenge, security. Security is the most critical feature of our engine since we're executing untrusted code. Earlier, we mentioned using execution context objects as a way to make our code execution stateful. But that was only one reason. The more critical purpose of the context object was to obscure the actual environment of the worker process from our users. In other words, the context object is a sandboxing mechanism that confines user code to an isolated execution environment. There are, however, a few JavaScript vulnerabilities that could be exploited. Rather than patch these manually, we leveraged VM2, a sandboxing library that guards against JavaScript escapes using custom environments with object proxies. Regardless, it's still important to have multiple layers of security, and therefore, we have a second sandboxing layer at the container level. There are various techniques that attackers can use to break out of a container and gain unauthorized control over a host system. These are known as container escapes. For instance, one such attack could mount the dev directory of a host, giving an attacker control of a host disk and network devices. A common solution that guards against container escapes is gvisor. Its runtime provides each container with a virtual kernel. However, as you can see in the table below, the runtime severely diminished the number of concurrent workers that we could support at a given time. Kernel virtualization is expensive, and it more than doubles the RAM requirements for our containers. We needed a much lighter weight approach. We significantly minimize the likelihood of container escapes by stripping away as many privileges as possible from our workers. We go into more details in our case study, but for now, we'll say that we've guarded against exploits by hardening our Docker container configurations. Now, if an attacker escapes a VM2 sandbox, it's statistically unlikely that they can also escape the container. Therefore, our configuration secures our system against malicious code while keeping sandboxing mechanisms as lightweight as possible. This allows our hosts to support up to 40 active notebooks and 200 active users. Now I'll turn it over to Judah for an overview of Pennant's final system architecture.
All right, thanks, Michael. Let's take a step back and look at the final architecture. There are three services. The user interacts with them separately. So let's step through them one at a time. The web server, collaboration service, and execution engine in rough chronological order. Our web server handles logging the user into their dashboard. The dashboard contains links to all of their previously created notebooks, as well as a link to create a new notebook. This service relies on a DynamoDB database, which can retrieve notebook names and IDs. When a user initially accesses a notebook, they're using another service, the collaboration service. A load balancer will route them to a WebSocket server called the provider server. Now they are connected to other users of the notebook or waiting for other users to connect to them. If the notebook is in use, the notebook is already in memory in the provider server. If the notebook is not in use, the provider server will fetch the notebook from the AWS S3 document data store. When the last user of a notebook disconnects, the notebook is saved back to the database and is removed from memory on the server. When a user submits code, that code is sent to a third service, the code execution service. Their code is routed through an API server to the correct Docker container dedicated to their notebook. This service is asynchronous, which in our case means the user polls for their results. These results first go to one client only, then are shared out to other users through the collaboration service. That concludes the presentation. Pennant was built by a small team, including Richard Cole, Marwan Zaarab, Michael Ricasa, and myself. We now open up for a question and answer session. Okay, so we have a first question here. What was it like working together as a team? Who wants to take that question?
It was this
Yeah,
is
Richard.
Richard speaking. It was essential to build this as a team. It was just it's too large of a project for one mind, and it was really important that we research every aspect from the security to the number of connections. If one was to try to do this by yourself, your technology would be outdated by the time you got around to implementing all the individual features. So it was a lot of fun to implement it in a team context.
Yeah, there was a ton of ground to cover, and definitely no one could do it alone. We definitely needed to leverage all of our efforts all the time for research and for implementation. But altogether, it's been a really fun process, and it's been great working with everyone on the team.
We have two more questions that just came in. First question is from Peter. What was the most difficult part to implement?
I can answer this one. Maybe this wasn't the most difficult part, but it definitely was one of the most significant challenges that we faced. And that was synchronizing real-time collaboration across various browsers and devices. So at first, it would only sync in regular Chrome tabs, but not in incognito tabs. Then we faced issues where it would only work in Chrome, but not when a tab was open in Firefox. So we spent quite a bit of time working together on this. We went through many different approaches. And then we finally found a solution that ensured synchronization between all browsers and browser modes. I think that was a great learning experience for all of us, but it also gave us a much needed confidence boost to tackle the other obstacles in our path.
It was interesting that we also faced problems with dealing with some of the technologies are implemented by incredibly small open source projects, incredibly small communities, which face a lot of challenges with the elegance of the API and the documentation sources. And then on the opposite end of the spectrum, trying to integrate with massive technologies like AWS, which came with sort of the exact opposite set of challenges in terms of how much documentation and the available configuration setups. That was led to quite a bit of whiplash building a cohesive system.
Yeah, I'll just add that in this, I also think that a difficulty was when running up against like system limitations. Like there were some servers that we could only work on in the cloud in certain operating systems, and that made it more difficult. Just was more time consuming. Like we would have to open up multiple processes on the cloud in order to test them. But that was just because they weren't compatible with the computer or operating system that I was working with. So that was difficult and frustrating. We have 2 more questions. First question from Show. How did you come up with this project? And I'm sorry, I'm actually going to tag along the second question because it's a very related question. Questions from Anthony. Why did you choose this project over other potential projects in the context of impressing possible employers?
Sure, I could maybe take the first one, how we came up with it. I think we spent a lot of time in the ideation phase. There were so many different things that we wanted to tackle. But I think we were all drawn to the idea of creating a collaborative application because it seemed to pose a lot of interesting challenges, more so than anything else that we were interested in. A second part of it is that my first experience with learning how to code was with Python and Jupyter notebooks. So I was trained as a data analyst first, and I thought that the ability to experiment with code cells and also take these descriptive notes in one place was such a cool thing to have, and it's such a great advantage that I thought it could be neat as well to bring that over to JavaScript or web development, the web development world, just because it would be really neat to keep your notes in one place and also have an easy way to collaborate with peers, in a really seamless way. So I think that's what drew us to Pennant in the first place, and definitely it delivered. Like it definitely delivered with all these really complicated problems. A lot of interesting stuff to solve for sure.
I was particularly interested in using the initially been interested in exploring the peer-to-peer models, and the fact that a lot of the underlying technologies can support both peer-to-peer and client server so elegantly was a bit of a shock. Depending on how you configure this, you would reconvert this back to a distributed peer-to-peer application really quite quickly. Just in terms of sheer technological excitement, that was a motivating factor for myself. And then the surface area of the project is quite big, and it touched quite a few interest areas: containerization, persistence, choosing the broad infrastructure choices, all sorts of big meaty problems that we wanted to dig into.
Marwan, you go.
Yeah, I was going to take Anthony's question. So why did you choose this project over other potential projects in the context of impressing future employers? So I think we chose this project because we recognize an opportunity to make an impact in the collaborative workspace. So with remote work becoming more prevalent, I think we saw a gap in tools that cater to both like code and markdown editing. So choosing this project wasn't just about creating another tool. It was more about contributing to this changing landscape and building something that could genuinely improve the way people work together. And I think we believe that it's an embodiment of the kind of thinking and practical problem solving that future employers will probably value.
I'm just gonna say one last thing to Anthony's question also. I was also particularly interested in working on something that was similar to like a Python notebook, because I thought it would be relatable to a lot of people and potential employees. A lot of people have heard of Python notebooks. So I thought it would be like more palpable to talk about and show. That was also a really big reason why I really wanted to work on this. We do have another question from Illuvia. If you could start over with the same project, would you change anything?
I think, oh, were you going to say something?
Just to fill the space, you should go.
Okay. Yeah, this is an interesting question. I think the one thing that I might have changed was maybe the amount of involvement each person had in various domains. That is to say, like each one of us, because this project is so large, each one of us became an expert, like in one vertical. Whereas I think I would have appreciated more time looking into other areas and trying those out. That's not to say that, I mean, pretty much every part of this project, everyone's had some involvement in some way. But yeah, I think if we were to do it over again, I think we would maybe manage our time in such a way that we get to try a little bit more of everything.
The state management was quite difficult to implement with React in terms of once an update has been received and integrated, sort of starts a large cascade of event handlers. And that took a shocking amount of time to adapt from the tools as they're written. So for one text editor, for one application, for creating a blog post or something, really to understand some of the results and challenges we were having took exploring source code line by line, and then building custom implementations of a lot of our tooling, which was a fantastic experience, but incredibly time intensive. So that was just sort of a broad learning curve in terms of our developments as engineers and how we manage time and expectations when building something that complex. The amount of times we thought, oh yeah, that'll be done in 48 hours, and then it presented quite a few iterations worth of challenges. That was significant.
Definitely a lot of rabbit holes.
Yep.
I think maybe something that I was struggling with throughout the project was I always like to try to at least plan to finish things early, even at like the expense of maybe simplifying it a little bit too much. And here I felt from the beginning like a kind of a time pressure, right? Because it's a fairly short window for implementing the project. So I just think like the more comfortable I would be from maybe doing a second project, I would probably actually take more time to delve a little bit deeper into exploring the problem before coding it out, or before trying to spike it. I think that may have helped solve some issues we got to, especially when we started trying to scale it at the end. We have another question. What are you most proud of in your work or surprised of?
the sort of moment of peak pride was once we figured out the need of the client side application, in terms of what it needed to synchronize states in the client server model, how robust it behaved once we finally cracked it, because we hit some fairly prolonged roadblocks in terms of being able to synchronize state remotely, and then the breakthroughs came hard and heavy after that. And then I've sort of been shocked at the lack of bugs in that space in terms of state synchronization. So once it took hundreds of hours of work between all of us to get that synchronization pattern established and documented, and then just how performant it was after that point was a real point of pride.
Yeah, I think something that stuck out to me was when the UI had come like far along enough that we could actually start carrying out usability tests and try it out on our own. And, you know, props to all those who helped us test Pennant. And it was cool to test it ourselves. Like, I remember Judah and I working on, you know, some data structures and algorithms problems using the notebook. And, you know, we were thinking, oh, gee, this is actually working. Like we could work in real time. We could take notes. We could paste pictures. Like, this is really neat. And it was, yeah, that was just like really rewarding to see it all come together and being able to use it for the first time. That was really cool.
There were some like really cool things that I just saw, like different people on the team were able to accomplish different like really cool technical feats. Like I'll say mine after, but at one point I was struggling a lot with getting the notebook to function correctly with JavaScript, because JavaScript has so many kind of very specific limitations with the language. I passed it off to Michael, and he was able to solve it. That was like really like awesome. So that was cool. That was like a great like teamwork example, but also like great that Michael pushed it through over the finish line. For me, I remember there's one time when we were dealing with some bugs, but I wasn't actually trying to solve the bugs. I was trying to optimize the code execution to make it faster by instead of writing the outputs to a file, which was like the typical way that we had seen in other remote code execution engines, where they would stream their results into a file. And then they'd have to open up a file in a file system, tear it down every time. So I was thinking, why don't we just use like an array that's in memory? It'll probably be much faster and easier to deal with. And so just delving in kind of to how to make that work. And just as a side effect, we ended up solving a couple bugs. That was a really good, like, feel good moment.
So many bugs. I remember that day. That was such a huge optimization that I think you cleared maybe like 4 or 5 cards off the off the bug board like with one go. So yeah, definitely a super cool. Yeah, definitely really be proud of. That's awesome.
All right, that was it for the questions. If you want to learn more about Pennant Notebook, you can go to www.trypennant.com, and you can open up your own notebook and try for yourself. Thank you so much for attending our talk, and yeah, thank you again. Bye-bye.
Thank you, everybody.
Thank you.
Thanks.